Today is 15th of April. I hope you remember, so we are discussing a very interesting new effect in neutrino oscillations, in particular neutrino spin and spin flavor oscillations due to weak interactions of neutrinos with the external matter, and this kind of mixing and oscillations can appear if there is a transversal in respect to neutrino propagation matter currents. This is a new effect that was proposed in our papers, and I am happy to discuss this in detail. So last time we derived the general expression for a particular contribution to the effective neutrino evolution Hamiltonian due to this effect, and I just only would like to recall. The neutrino evolution equation in moving matter and external magnetic field that has longitudinal respect to neutrino propagation component and the transversal one. Yeah? And the general form of this evolution equation, let's write it in the most general case. So let's consider neutrino state, neutrino flavor state. We consider two flavor and two spin neutrino state difference, so four different neutrino components. So let's indicate them like electron and muon. Yeah, this is electron plus, electron minus. This is a spin characteristic, then muon plus and muon minus. Yeah, transversal. This is neutrino state, and the evolution equation has the general form. So let's write everything accurate. This is the Hamiltonian that have the vacuum part, then in the flavor basis, the part that we discussed with you in our previous lectures that accounts for magnetic moment interaction of neutrinos with external magnetic field, both longitudinal and transversal components. Yeah, and plus the effect for the flavor matter. So, and we derive particular typical terms in this last contribution to the Hamiltonian. This is flavor neutrino, yeah? And this accounts for effect for matter at rest, this part we discussed in our previous lectures. Yeah, this is the flavor oscillation, mixing and oscillations in presence of media. Yeah, then it accounts for the longitudinal part of the component, matter current component, longitudinal in respect to neutrino propagation. Yeah? And the third part here, transversal matter current. So we derived in the last lecture contributions from effect of matter motion, yeah, to this effective Hamiltonian. So, and we have used the following notations. So, this in flavor basis matter term can be calculated as this combination of this is a flavor, this is, we use the indication, we call it, where V is the speed, indication for the speed of matter. And this guy is determined, and we have calculated it, in the mass basis. Of neutrinos. We have calculated this last time, yeah? Really, we calculate a typical term from which all terms of this 4x4 matrix can be reconstructed. And I will just recall it now, yeah? This was the final expression we derived last time. So we get that this part of Hamiltonian for mass states of neutrinos can be expressed as term matter at rest that was not of interest for us because we have derived it many lectures before when we discussed the mixing and installation in not moving matter, yeah? And here we put the following, this delta S, and we call it SM. So this is, in the mass basis, contribution to this particular part of Hamiltonian due to moving effect of motion of matter. All these terms are proportional to the longitudinal or transversal current components or corresponding speeds of matter, yeah, in respect to laboratory frame. Yeah? So we have a laboratory frame, neutrino is propagating nearly with the speed of light because it's a relativistic particle, and also matter is moving with the speed that it. Yeah? It could be fast moving or not fast moving, etc. So, and for this is effect of motion. Effect of matter motion. So, and for this we obtain the following. So, I just write for completeness. So, delta EE plus plus delta E plus minus delta E mu plus plus delta E mu plus minus delta E minus plus delta E minus minus delta E mu minus plus, then delta E mu minus minus, then delta plus plus E delta plus minus mu E delta plus plus mu and delta plus minus mu and the final line here, delta mu E minus plus delta minus minus mu E delta mu minus plus delta minus minus mu. Okay, that is the most general part of the expression, and for these deltas, we get the following. This was the final expression last time: S prime, S and, oh my god, I'm sorry. So I can't use it, I suppose. Yeah, S prime equal plus minus 1 equal plus minus 1, or plus minus, both. And alpha, okay, and we shall use alpha and alpha prime equals to 1 or 2, both, yeah? So, and we get for this delta alpha prime the following expression. I just recall that matter is composed of neutrons, yeah? For simplicity, yeah, of course we can use the same derivation for any matter composition. We can also include electrons, protons, all of them together, or just any component of matter. But for simplicity, I use it matter composed of neutrons. It's more or less applicable to real media over neutron stars, which are of 90% composed of neutrons. Yeah, the rest 10 are protons and electrons in equal amount. Yeah, from the point of view of weight, it's 90% of neutrons, nearly 10% of protons, and the same amount of electrons, but they give nothing in the mass, you see, because they are much more lighter than protons, yeah? Okay. This Fermi coupling constant divided by 2 divided by square root of 2, and 0, 1 minus the speed of matter of neutrons squared. Yeah, so this is this term accounts for Lorentz transformation from the laboratory frame to the frame related to matter being at rest. Yeah. So there are 3 reference frames: the laboratory frame, the observer, or just a person who makes all these calculations. Yeah. Then there is a reference frame related to neutrinos, and there is the third partner who can move his matter. And there is a reference frame rest frame of matter as a whole. Understand? Yeah, this is a, so we have a tank or a carriage of neutrons or electrons or protons, but now they can move, but in general they are confined in one tank. So it means that this is the general speed, average speed of the tank of particles of matter. But inside they can move depending on the statistical distribution function. But this is average speed, average speed. Yeah, it can be calculated by a particular speed of a particle of average integrated with the distribution function. Yeah, statistical distribution function. Yeah. So, okay. And when we are saying that matter is not relativistic, it means that the tank of matter is moving slowly. But inside this tank, each individual particle can move even with the speed of light, understand? But in general, if it is confined in this closed volume, and its volume is moving with a slow speed, the matter will be not relativistic, as we say. Yeah? This is not a particular velocity of a neutron. This is an average velocity. Yeah? Okay. And then we get the following. U alpha S transponent 0, 0, 0, 2. The longitudinal part of the matter velocity plus 0 gamma alpha inverted gamma alpha prime inverted 0. The transversal matter velocity U alpha prime S prime delta lambda alpha, sorry. Okay, that was the key expression that really shows that the transversal motion of matter with which neutrino interacts due to Fermi coupling constant, the big interactions of transversally moving matter, generate transitions between different spin states. Understand, yeah? So this is spin flavor mixing and oscillations in transversal matter currents. The effect that was first proposed in my paper in 2004, and on the basis of classical treatment of neutrino spin evolution, using the Barman-Inschel-Telegde equation generalized for the case of matter is present. And then in our paper with my student and postgraduate student, Pustoshny, we have performed detailed quantum calculations. So, now let's go further. Let's go further and let's write. So we are interested in the probability of spin and spin flavor oscillations in moving matter you understand what I am meaning, and constant magnetic field So you understand, yeah? So we are interested now in writing and solving the most general case when there is arbitrary entered in respect to neutrino propagation constant magnetic field, which produce the longitudinal and transversal components in respect to neutrino propagation, and also matter is moving in arbitrary direction in respect to neutrino propagation. Yeah. So just we have to make several steps. So just using the formulas that we derive, we can write an effective Hamiltonians in the mass basis of neutrinos. Yeah. Now we have to formulate and to solve this problem. We should go make a transition to the flavor basis. Yeah. Okay. So the transition to the flavor basis, neutrino flavor basis. It's very simple. So we have to write flavor neutrino is a superposition of neutrinos, mass states of neutrinos. Yeah, alpha F where the electron muon, alpha 1 or 2. Yeah. So, okay. The mixing matrix is determined by the mixing angle theta okay, and for particular case of 4 neutrino species, 2 flavors and 2 mass states of neutrinos, this U is very simple matrix, cosine theta 0, sine theta 0, 0, cosine theta 0, sine theta minus sine theta 0, cosine theta 0, 0 minus sine theta 0, cosine theta minus sine. Yeah. And the evolution equation, once again, in the flavor basis, reads as follows: I d nu flavor dt equals to where this is related to the this is a flavor, this is a mass basis. I am not putting concrete indices for any parts of the evolution Hamiltonian. This is the prescription how to make transition from the evolution of the mass states in the mass basis to the flavor basis. Yeah, for any contributions we are discussing in considering for the vacuum, for effect of for the part of the Hamiltonian that accounts for matter at rest, for the part of the Hamiltonian that accounts for neutrino magnetic moments interactions with the constant magnetic field. If you remember, we also introduced the magnetic moments initially to the mass states of neutrinos, because we would like to describe totally all the properties of neutrinos when they can be considered as the real particles with the well-defined masses. So when we decided to introduce the electromagnetic properties of neutrinos also for the mass states of neutrinos. But of course, especially in the previous years, people sometimes started discussing electromagnetic properties from the flavor basis. But from my point of view, and lots of people just follow this prescription, so first determine electromagnetic properties for the mass states of neutrinos, and then make transition to the flavor basis and obtain results that are familiar for experimentalists, because they deal with the flavor neutrinos. They are detected, yeah? They interact. And so we know how to describe neutrino interaction with the detector or for the flavor states, yeah? Okay. So indeed, we can use similarity between the tradition of Hamiltonians that describes neutrino electromagnetic interaction with the magnetic field and weak interaction with moving media. So we, in the previous lectures this semester, we discussed and derived point by point how to make this transition from the mass basis to the flavor basis when we introduce neutrino magnetic moment interaction with magnetic field for the mass states of neutrinos. Now we introduce, we shall compare two Hamiltonians in the mass neutrino basis, electromagnetic and weak interaction Hamiltonians, and using our knowledge how the Hamiltonian for the electromagnetic interaction were generalized for the flavor basis, we use the same prescription, and we will not follow that detailed calculations, but we shall write immediately the answer using the similarity. So now we would like to compare two Hamiltonians. So compare two Hamiltonians. One for electromagnetic interaction, and another one of our particular interest now, weak interaction with moving matter. So the Hamiltonian that accounts for interaction with magnetic field has the following form: mu alpha prime, nu bar alpha prime. This is, I just start with the mass basis, yeah? Alpha and alpha prime stands for 1 or 2. This is a mass states of neutrinos, yeah? So we introduce sigma multiply by the strength of magnetic field vector nu alpha plus conjugacy part, when this sigma can be written as a follow. So it's better to write not a vector, but say I, yeah? 0, 0, I, yeah? Okay, this is the Hamiltonian for magnetic field interaction, and now effect of matter that I make a mistake, or not a total mistake. Okay, this is the speed of matter. It has the following form: V equals to Fermi coupling the invariant number density of neutrons nu bar alpha prime V gamma V alpha, where G Fermi with wave equals to just a normal coupling constant, Fermi constant, divided by 2 divided by square root of 2, and n equals to n0 1 minus v squared. Yeah? This is where n0 invariant number density of neutrons in our case, yeah? So, and now we know how this procedure transform this Hamiltonian. We derive it, and just one, by the previous lecture, we have written the final result for this particular transition from the mass states to the flavor states using this prescription. And now I just go further and apply the same procedure to the Hamiltonian that accounts now for meta effect, or meta motion effect, because this is proportional. I am not including the effect of meta at rest, because it was discussed in many lectures before. Yeah? At the end, I will just add effect of meta at rest effect just by hands to the final expression for effective Hamiltonian. Yeah? So, plus, yeah? So for I think that probably I have to repeat also the part that is related to magnetic field, because just the next step we shall use both effects from magnetic fields plus effect of metamotion. So for the effect of magnetic moment interaction with magnetic field, we get the following in the flavor basis. In the flavor basis, we have the following. Minus mu gamma EE, B transversal, mu EE. This is effective magnetic moment of electron neutrinos, effective, that is expressed in terms of magnetic moments determined or introduced for the mass states of neutrinos. And I will just write what it, in a moment what it is. Minus mu divided by gamma E mu, B longitudinal, mu E mu, B transversal. This is the transition magnetic moment in the flavor neutrino basis. Transition magnetic moment that couples neutrinos of different flavors, of electron and muon neutrinos. Yeah, understand? So then here is again mu EE multiplied by the transversal magnetic field. This is mu divided by gamma EE, B longitudinal, mu E mu, B transversal, and mu divided by gamma E mu B longitudinal. So the next minus mu divided by gamma E mu. Indeed, I am saying divided by gamma. This is, if you remember, this is just a notation. This is not a mu divided by gamma. This is more complicated structure. Yeah, I just invent these notations because just to understand the value is proportional to magnetic moments and inverse proportional to gammas. Multiply different terms multiplied by different combination of mixing angles, cosine, sine of mixing angles. Yeah, I'll just recall. This is a result of this transformation. If you just make this transformation, you will get these guys. So mu E mu B transversal minus mu gamma mu B longitudinal mu B transversal, and the final line here in the effective Hamiltonian, accounting for magnetic moment interaction with the longitudinal and transversal magnetic fields in the flavor basis mu gamma E mu B longitudinal mu B transversal, and the final mu gamma mu B longitudinal. Okay. Where? We just write it, but I just recall where the effective magnetic moments in the flavor basis. So we have several terms here: mu E, mu E mu, E mu mu, E mu. Okay? So the effective magnetic moment of the flavor neutrino, of electron neutrino, effective magnetic moment, is expressed mu 1 cosine squared theta plus mu 2 sine theta sine squared theta plus mu 1 2, this transition magnetic moment in the mass basis, yeah, transition magnetic moment, sine double mixing angle. So then magnetic moment for another flavor neutrino is similar but not. So mu 1 sine squared plus mu 2 cosine squared minus mu 1 2 sine double theta. Yeah. And the transition magnetic moment in the flavor basis mu E mu equals to mu 1 2 cosine double theta plus 1 divided by 2, the difference of diagonal magnetic moments in the mass basis, multiplied by sine squared or sine double theta. Yeah? This is effective magnetic moments in the flavor basis. If we introduced initially the magnetic moments for the mass states, it's a result of this transformation. This is the mixing. Yeah. Okay. What about these terms? this kind of terms. Let's write these expressions. We get the following. First, EE equals to mu11 divided by gamma 1 cosine double theta plus mu22 divided by gamma 2 sine squared theta plus transition in the mass basis mu1 2 multiply by double theta. Yeah. You remember this is the gamma factor for neutrino mass 1, mass 2, and this is what it is. This half sum. So this inverted guy equals to half sum of inverted gamma factors for the mass states of neutrinos, 1 and 2, yeah? No, sometimes I just write here 1, 1, but this is not needed to write 1, 1, yeah? This is 2, 2, you understand? If you use this general, if you would like to follow similarity, but so there is no need, yeah, to write. Okay, then mu gamma. What is important? Why we just restore just in this term? This is not a ratio. Yeah, of course, you understand. This is like a notation, but it's recalled that all terms here proportional to sum of magnetic moments in the mass basis divided by some gamma, the corresponding gamma. That's why we use this. It seems a little bit tough, yeah, but it's when you just look, you immediately understand what is the scale of this value. Yeah? It's proportional to some magnetic moment divided by some very, very big value, because gamma is very big. For any of these gammas are very big, yeah? Because we are considering relativistic neutrinos. So E mu equals to mu1 2 divided really to nu1 2 cosine double theta plus 1/2 mu2 2 divided by gamma 2 minus mu1 1 divided by gamma 1 sine double theta, and the final guy of this term of this type mu gamma mu equals to gamma 1 1 really divided by gamma 1 sine squared theta plus mu 2 2 divided by gamma 2 cosine squared theta minus mu 1 2 divided by gamma 1 2 sine double theta. So what is interesting, that this term stands and relates two different opposite, I would say, flavor states, yeah? And it is not zero if the transition magnetic moment in the mass basis is not zero, or if even it is zero. But there is another chance, if the magnetic moments for the mass states are not equal to each other. Understand, yeah? So this is very interesting, tricky, yeah? And you can think about what kind of transitions in the flavor basis that are of interest and understandable for an experimentalist, is accessible for observation, can appear. What kind of effects you should account for if you are considering, for example, some astrophysical environments where neutrino transitions and oscillations of different types can appear. Understand? Yeah. So. Using this analogy, so the similarity of Hamiltonian in magnetic field and Hamiltonian in moving matter, we can write similar expressions with a particular new notations, obviously, for the effect of neutrino interaction with moving matter, using this similarity. Yeah? So, and I just write, this is a new result that I am writing now for the first time for you. Yeah? So finally, we get the following, that the Hamiltonian contribution of the effect of neutrino interaction with moving matter, and I'm just fix your attention that we considering the effect of even moving matter, because matter at rest we just know how to write it, we just already calculated it. Yeah? Only effect of interaction of neutrinos with moving matter, not at rest. At rest we will add. So this is the Fermi constant with the wave divided by 2 square root of 2, and the number of density of newtons of our matter. This is 0. This is eta gamma EE. Transversal speed of matter. Yeah. What is this guy? I just write in a moment. 0 eta gamma E mu V transversal. Then the second line. Eta gamma EE V transversal, double eta EE 1 minus V transversal, longitudinal, the next term here, eta gamma E mu V transversal, это E mu. Here, matter at rest. What I have just claimed, I put by hands this one. This doesn't depend on the velocity of matter. It's the effect of matter at rest. This is a term that contributes to the famous Mikheyev-Smirnov-Wolfenstein effect, resonance amplification of neutrino flavor oscillations in presence of matter that is not moving in respect to laboratory frame. This term we have already discussed when we were considering neutrino mixing and oscillations in non-moving matter or non-relativistically moving matter, when V, longitudinal, transversal, or both are much less than 1, when we can neglect this term. And also we neglect these terms when we were considering effect of neutrino scattering on matter at rest, or slowly moving, not relativistically moving matter. Because the effect of matter motion is important when V is much bigger than is close to 1, yeah? If it is much less than 1, it means you can forget it. But only a relativistic effect is important, yeah? But
In some cases, not only relativistic, but it's better to have high velocity matter to see this effect. E mu, V transversal, 0, eta gamma, mu, V transversal, and the final line here, eta gamma, E mu, V transversal, eta E mu, eta gamma, mu, V transversal, double eta mu, and again 1 minus longitudinal part of matter velocity. Again, this is matter at rest. Matter at rest effect. Yeah? So, now I would like to specify all the used notation. These etas are very, very EE. So, for curiosity, I express it using the notations that we use for the effect of magnetic moment interaction with the magnetic field. But normally, this guy is equal to 1. But how it can be obtained? It is equals to mu EE when mu 1 equals to mu 2 equals to 1, and transition magnetic moment equals to 0. And that's for curiosity. So just to show the link or relation between the notations. I said that this structure is reproduced in a very similar form of calculations that we performed for the case of magnetic moment interaction with magnetic field. And all notations can be translated like this. Yeah? So mu eta mu also equals to 1, and the most simple guy equals to mu E mu when we put mu 1 equals to mu 2 equals to 1, and mu transition equals to 0 equals to 0. Oh my God. So just instead of this, this, and where is it? Oh no, it should be 3. EE. I don't see where is EE. Mu, and where is EE? EE. Yeah? So I can put zeros here. So it means that it should be 0, yeah? And this should be 1. But, okay. And the rest expressions, yeah, are the following. Plus. And eta gamma EE equals to, again, I just EE when mu 1 equals to mu 2 equals to 1, and mu 1 equals to 0 equals to cosine squared theta divided by gamma 1 plus sine squared theta divided by gamma 2. Okay? So the second term of this type, eta mu mu, equals to mu gamma mu mu, the same, equals to sine squared theta divided by gamma 1 plus cosine squared theta divided by gamma 2. And the third one, term of this time, eta divided by gamma, E mu, transition part, in a sense, this is mu divided by gamma, E mu, again with the same prescription, two magnetic moments are equal to 1, diagonal and off diagonal 0, equals to sine double theta divided by gamma 1, 2. So we obtain the final expression for the effective evolution Hamiltonian in the flavor basis, accounting for neutrino magnetic moment interaction with the longitudinal plus transversal magnetic fields, and accounting for neutrino electron muon neutrino interactions with moving matter composed of neutrons, in the case where matter is moving in the direction arbitrary to neutrino propagation. So there is a longitudinal and transversal matter currents in respect to neutrino propagation direction. Yeah? So this is a complete evolution equation, and now we can try to solve this equation. Of course, we can try to solve a complete story with using all possible transitions between each of 4 states to another 3. Yeah? In some places we have zeros in the effective Hamiltonian, so there will be no transitions. But if we just sum up all terms, there will be all terms all together give not zero terms in total. Of course, it is probably it is possible to write this solution, but I would like to consider now a specific cases of transition between one particular neutrino state to another particular state, just to see possibility and to feel the scale of possible effects. Of course, we are now interested in effect of spin or spin flavor mixing and oscillations under the influence of interaction due to neutrino interaction with the moving matter. This is effect of particular interest for us. It's a new effect. So let's consider particular cases and start with one. So the particular case, neutrino spin oscillations engendered by transversal matter currents and magnetic fields. So we consider neutrino electron left. We use this notation due to interaction by magnetic moments with the transversal magnetic field and weak interaction with transversally moving matter. Yeah, that is meaning. And we consider spin oscillation without change of flavor. So it's electron right. This is neutrino spin oscillations. Mixing oscillations. So this kind of transitions can be induced or produced by magnetic moment interaction with transversal magnetic field if it is not zero, and also weak interactions with transversal currents. And from the general 4x4 equation, we use 2x2. Yeah, the transitions between only two fixed states, initial and final. Okay? And we can write from the general expression the following: I d over dt. Now we have two neutrino states, left neutrino electron, right. So I would like to stress once again, without change of flavor, because next example, net point, we shall consider when there is a change of flavor, for instance. Yeah? So this is spin, not flavor, oscillations. Yeah? And we have to select from these 4x4 Hamiltonians only 2x2 that corresponds to this mixing between these states. Yeah? And it's just, and I would like also to recall that initially we just use the following definition for the flavor state. We just write flavor plus minus electron, yeah? Then plus muon and muon minus. Yeah? Now I inverted. So this is neutrino left, and this is neutrino right. Yeah? And now, so we change the positions, you understand, yeah? Now, if you just use the same, transparent, yeah? If you just use the same prescription, the following formula should be changed by exchange of positions of terms in the different lines and different columns, understand, yeah? Because now it is more common just to write left to right, and not right to left. Well, but it's the point of taste, yeah? Not, okay. So, it's 2x2, mu gamma EE, B longitudinal, plus eta EE. By the way, it is 1, if you remember, but for completeness, I just write this G wave, the density of neutrons minus V B vectors. Then this is the first term of the first line, the first column. Then mu EE B transversal plus eta gamma EE coupling constant wave N V transversal. The second line, two terms in the second line. The first column, mu EE B transversal plus eta gamma EE G waved and V transversal. And the second line, the circle column, minus mu gamma EE B longitudinal minus eta EE, that's equal really to 1, G waved, and 1 minus V beta. Okay? And then we write electron left, electron right. By the way, if you just compare this expression to the previous one, what I have done, I just added to the total derived that Hamiltonian on the previous transparency or slide, yeah? unit matrix multiply by constant value to make it more symmetric. Because if you are interested only in the solution for the Neutrino oscillation problem, you can add to Hamiltonian any value multiplied by the unit matrix. So you can change correspondingly diagonal elements. If you add here something, you should add here or extract. And I just make it to make it more symmetric. Don't confuse, because if you compare this with the 4x4 Hamiltonian, you will see there were some zeros, there is no zeros. It means that I close the zero, adding something here, and simultaneously added something here, if you remember. There was double term, 2 multiplied by something. Now there is no 2, because I just extracted something that 2 become 1, but added here. Understand, yeah? I think if you compare, you will see. And also I make this change. Left, right, but before was right, left. Yeah, understand, yeah? It's transparent. Well, what we can see now, what we can see. This is effect of matter at rest. And also this one. This is effect, eta equals to 1. I just, okay. This is normal expression. If you just switch off the velocity of matter, this is exactly what we derived for the case when we considered neutrino flavor oscillations in matter composed of neutrons, but we also added electrons and protons, if you remember. Now I am not interested in these complications. So what we can see, really, we discussed several times. So the weak interaction with the transversal matter currents acts as the magnetic moment interaction with the transversal magnetic field. And the result is neutrino spin oscillations, not only in transversal magnetic field, but also in matter with the transversal current component on zero. This is a new effect. So you can switch off magnetic field or magnetic moment, or in general electromagnetic interactions, and there is a mixing between left and right-handed neutrinos without change of flavor, if you wish, due to weak interactions with transversal. Also, it is suppressed. That's why I just used not A, B, just symbols here. I put this notation to recall that this term is suppressed by big value of gamma, of a relativistic effect, or relativistic gamma factor of neutrinos, mass states of neutrinos. So, contrary to the effect of interaction with transversal magnetic field, it is not suppressed. In the case of magnetic field, the longitudinal magnetic field is suppressed contribution. This is the contribution to the Hamiltonian due to interaction of neutrinos with the longitudinal magnetic field. It is suppressed by gamma in magnetic field case. But in the weak interaction, transversal component is suppressed. You see, understand? Yeah? And longitudinal part is not suppressed. This is matter, is not suppressed. Yeah? And also this guy can be very, very small, depending on what is the value. Of course, if V is 0, it is nothing. If V is small, in any case, it is small contribution because the modulus V and B is less than 1. Yeah, no, less. Obviously, yeah, because we use the reference, the notation C is equal to 1, yeah? So even it cannot be equal, yeah, because the matter can't move with the speed of light, obviously, because it's a massive object, and neutrino is also a massive object. It cannot beat the speed of neutrinos. For sure, it's less than 1, but it could be very, very close to 1, yeah. And so it means that in some cases this term can cancel out. When the speed is very high and the neutrino is supposed to be very relativistic, this value can be very, very, very small. V multiplied by B can be very close to 1. Of course, it depends on the direction of motion, you understand, yeah? Of the cosine, yeah? Well, and the solution of the problem. Let's write the solution. The probability of neutrino electron left, we just use this, yeah? Oh, without neutrino electron right, oscillations. The probability. It's I just write this probability in the general form, obvious form. We just converted the evolution in time to evolution in space, yeah, obvious because no, you know this, yeah. So this is probability to see neutrino of the another type once neutrino travel a distance x from the source, yeah. And it has the following general expression: E effective. I just determine what is in a moment. E squared effective plus delta squared effective multiply by the guy that is varied according to sine squared depending on the travel distance. Effective length, yeah? Where? The effective length just is straightforward from the explicit form of Lagrangian, effective Hamiltonian. By definition, in general, it is like E effective squared plus delta squared effective. And this E effective, just looking on an explicit form of the Hamiltonian, exact form, we write that is modulus of mu E B transversal plus eta gamma E waved coupling constant G and V transversal. This is vectors. Important, this is vectors. This is modulus of the sum of two vectors, yeah? So we have to also to take care about the direction of orientation of the transversal components of the magnetic field and the speed of matter. And delta equals to, again, modulus effective mu gamma E vector, again, longitudinal magnetic field plus eta E that equals to 1. I don't know why we are including these notations. This is a vector, this is vector. So this is neutrino is moving in this direction, neutrino, yeah? This is the speed of neutrino, and this is vector of the longitudinal magnetic field. Again, this is a sum of two vectors, proportional to the longitudinal magnetic field and proportional to longitudinal speed of neutrino. Because we fix the direction of propagation of neutrinos just fix it, this axis, as the axis of neutrino propagation. That is the end of the story. We derived and we see that the amplitude of oscillations, this is the amplitude of oscillations. These oscillations due to sine squared of something that depends on the travel distance, varying at sine squared of x multiplied by some fixed value. And this is the amplitude. When there is a resonance, when delta is very, very small, the resonance in oscillations when the amplitude of oscillations go to 1. It means that the resonance condition is E effective much bigger than delta effective. As usual, we always obtain something like this. In the case of flavor oscillations in the non-moving matter, we obtain the same. Yeah. Also, when we considered neutrino mixing and oscillations in only in magnetic field without effect of motion, we again get the same. But here we just incorporate to what we have already studied when we considered neutrino spin and spin flavor oscillations. Well, in our case, we are dealing only with the spin oscillation without change of flavor. In the magnetic field, we also discussed the resonance. Now we can switch off effect of matter motion, just cancel this term and this term cancel out with the speed of, this is speed of, speed of matter, yeah? And we shall get the previous result when we consider neutrino spin oscillations in the presence of matter at rest. And now we can play the game. We can find different options when this effect is realized. And probably we shall discuss it next time, I suppose. Yeah? Thank you very much.